Hello.
Hi.
Hello.
Hello. How are you guys?
I'm good. How are you?
Uh, doing okay. Maybe more one day, but I'll get through it.
Um,
Yeah.
Recording in progress.
Yeah, I passed most of them. I did not do too well. I did not do well on one of them, but I'll make it up. Yeah.
um, sorry
See.
about
So
that.
no, it's okay. It's okay. Yeah. Mhm. Yeah.
We we had the quiz today.
Oh, how did that go?
Well, it was a little bit different than expected. It was like covering IR, and instead of like interpreting the like the graph where you have
Yeah.
to see like you have to evaluate the points and see like what functional groups are there, they gave us like the functional groups itself and like the numbers. So I'm kind of still relatively new on the idea.
Mhm. Oh, like the IR stuff, like how to interpret them,
Yeah.
data, the numbers, everything, and everything.
Mhm. Yeah.
Uh, yeah, we could go over that, but I think I'm gonna go over like stereochemistry stuff first, and then we could go over the IR stuff after that.
Okay,
Mhm.
that's cool.
Yeah. So let's see here. Smooth images, smooth images. Okay. Let's see. Okay, share screen. Let's see. Okay. So this question here is asking for enantiomers, like they have the same physical properties and cannot be separated using typical lab methods. In general, separation can be achieved by converting a racemic mixture to two different diastereomers, which can then be separated. Given a racemic amine, racemic meaning that you have a one-to-one mixture of enantiomers, and the chiral center at that carbon. So the racemic amine is saying that this amine here, one half of the mixture is a wedge, the other half of the mixture is a dash. Right. And a chiral resolving agent, tartaric acid, identify the two diastereomers formed. So let's go over the differences between enantiomers and diastereomers. Enantiomers is when all of the chiral centers in the molecule change. So if I give you this structure right here, all the chiral centers flip, right? This wedge ethyl flipped into a dash ethyl, and this dash isopropyl flipped into that wedge isopropyl. They would be considered enantiomers. Diastereomers is going to be when some chiral centers change, but some stay the same. So for example, if I give you, like, let's say the same first, but this time the second molecule is going to be this right here, right? Where we see that the wedge ethyl stays as a wedge ethyl, but the dashed isopropyl stay flipped to a wedge isopropyl. So some chiral centers change, some stay the same. Diastereomers, right? Some chiral center change, some stay the same. And for enantiomers, all chiral centers flip. Okay. So for this one right here, we're gonna get two dice. And let's identify the chemistry of the two dimers. The mean is S. I mean, tartaric acid is S. Tartaric acid is R. The diisomers can be separated by dissolving in base, HCl, crystallization, physical properties. Okay. Yeah, so that's the definition of enantiomers and diastereomers. But I haven't learned about chiral yet, so I'm not sure what this is asking for. And this is more of a lab thing. So I haven't learned about this topic yet. Like chiral resolving agent here, but this is what enantiomers are, and this is what diastereomers are. Identical structures would be if all the chiral centers stay the same. All chiral centers stay the same. So for example, if we have this structure, we could flip it around to get this structure right here. So even though it looks flipped, right, they're identical, because look at the backbone of structure, the backbone of the structure here. We just flipped it upside down, which would flip everything as well, right? This wedge ethyl, when it gets flipped upside down, can be inverted to a dash ethyl. This dash isopropyl, when it gets flipped upside down, it's gonna get inverted to a wedge. It doesn't get inverted; it stays as like its original bond, like nothing changes to that bond. But when we flip it into the view what is going towards us now. So this is when the 3D model kit comes in handy. But you can just imagine in your upside down, um, you're making this like go towards you, and making this away from you. Right. Okay. Am I cutting out still? Okay. So for this one here, when they're asking for which ones are identical, they have the same molecular formula, same connectivity, and the consensus will stay the same. These two here are not going to be identical because they don't have the same spatial arrangement, right? If you look at this chiral center here, that's going to be S. This chiral center here is be R. So if you look at this one here, this is going to be 1, 2, 3. That's going to be R, which is different than S. This is going to be S, right? Which is different than R, right? So they are not the green chiral center here flipped, and the pink chiral center here also flipped. So if all chiral centers change, what would these two be to each other? Right? They would be enantiomers to each other. Right. Okay. So if we look at this one right here, this is gonna be 1, 2, 3. That's S. That's gonna be 1, 2, 3. It looks R, but it's actually S. So that's SS, RS. Let's look at this one. This pink one here is 1, 2, 3. That's gonna be S. This is gonna be 1, 2, 3. That's gonna be R. S, R. This is S, S. This is R, S, R, S. Let's see. Yes, identical. Nope, that's diastereomers. Yeah. Okay, try. Hold on, if I rotate it this way, it's gonna flip it that way. No, that's different. This is also different. Same connectivity, boom, boom. Everything is 2 apart. R, S, R, S. Okay, so the identical ones would be this third one and the fourth one right here, right? Because if we look at the green chiral center, the one with the bromine, they stay as R. If we look at the pink chiral center, they stay as S, right? So this structure here is identical to this structure because they have the same chiral center, and also you could visualize that by rotating the whole structure clockwise. And when you rotate it, you're going to get the same exact structure right there. Yeah. So it's going to be the last tail. Right. Yeah. Yeah. Okay, so now let's go over IR stuff. So IR is going to show you the functional groups present for an unknown compound, right? And it's going to show you that by unique peaks in the graph. It could either be like broad peak or sharp peak at a certain length, and then that's going to show you what functional group is present. So I'm going to show you my IR chart that I look at, or think about when I think about IR here. It's going to be which is this one. Here. So the region at 1500 and below is going to be called the fingerprint region, right? That fingerprint region, you can basically ignore. You have to think about it when you're determining the functional group. If you see a sharp peak at around 1600 in the IR, then you know that you have an alkene present. If you have a sharp peak at around 1700, you know that you have a present. Around 100, then you know that you're going to have a triple bond present. This is called the triple bond region. So it could either be an alkyne, C triple bond C, or a nitrile, C triple N. At 2700, if you see a sharp peak around there, that's the aldehyde peak. So that means that you have an aldehyde present in your molecule. And then this base peak at around 3000 right here is always almost going to be there. Right. I have who on IR as well, so we could try that like at the end of the session or like tomorrow session. Um, but for now, let's just go over like what IR mean, what they represent. They just show you what functional groups are present in a non-compound. This is always going to be molecules an sp3 carbon hydrogen bond. Right. So that 3000 base peak right there. Now let's go into the 200. If you see a big peak at 33, it's not sharp like this, that could either be an alcohol, molten alcohol, OH, or a secondary amine, right? But this amine is attached to two other R groups, right? If you see a fang-like looking structure here, then that's going to show you primary amine, meaning that you have an amine that's attached to one other R group, like that. If you see a sharp peak at around 3300, then that means that you're gonna have a terminal alkyne, right? An sp carbon hydrogen bond. So if you have a terminal alkyne, you will always see these two peaks paired up with each other, right? You'll always see the sharp peak at around 2100 to 2300, and that sharp peak at around 3300. If you have a terminal alkyne like this, but if you just have an internal alkyne like this, where the alkyne is an alkyne, you will get this peak right here. You will not get this sp carbon hydrogen peak. You will not get that sharp peak. There's no hydrogens attached to this alkyne right here, right? If you see a sharp peak around 3100, then that shows you sp2 carbon hydrogen peak. So in most cases, in most examples, this peak will always pair up with the 1600 peak, right? Where let's say we have this alkene right here, the carbon double bond carbon. The carbon double bond carbon is represented by the 1600 sharp peak right there. The sp2 carbon hydrogen bond is represented by that sharp peak at 3100 right there. Right. So these are all the peaks that I remember for IR, where sometimes they might not even give you the graph to interpret. Sometimes they might give you a range, like around 1610, there's a sharp peak around their wavelengths, right? And then you just have to know that that sharp peak is going to represent a carbonyl, or a sharp peak around 1750, that's going to be a carbonyl, right? Uh, Wait, 1600 is alkene. C double bond carbon. 1700 is going to be carbonyl, carbon double bond oxygen, like that, right? Or you might even see broad peak at around 3350, right? And you see a broad peak right there, and that's one hydrogen, then it's most likely going to be an alcohol present, right? So a lot of this is just like memorization, but you will able to memorize this by doing a lot of practice problems related to IR, like what functional groups are present given this IR, or predicting molecules with like by using IR and NMR. So when you're first like doing these IR problems, like have this chart by hand and then do practice problems. And then as you do more practice problems, try like doing the problem without looking at the IR graph, and then only look at it when you need to, like when you struggle for a little bit. Right. Was that the question you had, Elysia, for IR? We could try like Kahoot, like at the end of the session or tomorrow session for IR. Mhm. Oh shoot. Hello, hello. I think your mic not might not be working. But we could do the Kahoot tomorrow because I think that's when Kathy learns that tomorrow. So then I could go over this more tomorrow and then do a lot of practice with IR tomorrow. Right. Yeah, I see like muted, but I think your mic is not working or not connected.
Hello, can you hear me?
Oh, yeah, I can hear you now.
Okay, sorry. I don't know what happened, but I sent um a practice
Uh-huh.
problem. Um, and
Yeah.
this may have been the one that they gave, but um, I I'm not sure if I got it right.
Yeah. Let's see. Let me check your folder.
Oh, I
Mm,
sent it through the Discord. Is that okay?
Oh, yeah, that's okay. That's
Yeah, because
okay.
I
Yeah.
kind of just drew it
Let me
out.
check.
I didn't have like an actual
Uh-huh.
photo of it.
Yeah. Oh, yeah. For quiz. Wait.
Yeah.
See. Oh, I see. I see it. Okay. Okay. Save. Um. Ability. Okay. Share screen. Okay. Okay. Yeah. Which region does the following molecule not show IR signals? So, to approach this problem, what I would do first is determine what functional groups are present and how that will show up in the IR. So,
Mhm.
as practice, what functional groups do you see present here?
Um, I see an alkene.
Uh-huh.
I see, is it a phenol? A phenol?
A phenol present, right? An alcohol attached to um, a benzene ring. So there's an alcohol present as well.
Not sure about the carboxylic acid. The one with the carbonyl group.
Yeah, the one with the carbonyl group right here. If it's next, if it's like if it's two R groups next to it, like that. If it's sandwiched between two R groups, then this. Okay. Um, when we think about carbonyl, there's a lot of carbonyls.
Mm-hmm.
Right, carbonyl is a big umbrella term for a lot of things. Shown is when we have sandwich that carbonyl high, you can think of as a hydrogen hiding, right? So one R group, one acid is when we have one next to that carbonyl. An ester is going to be an OR group, carbonyl. Side is going to be NH2 or NR2 or NRH or NR2 next to the
Mm-hmm.
carbonyl. Um, you could have when you get into one, you can see acid halide or anhydride. Right, but there's a lot of carbonyls that you can have. Carbonyl is just a big general to represent a lot of functionals. Where if we have any carbonyl, right, that will still show up in the IR as the same, like around the same area.
Okay.
Um, right, and then we also see that as well, like a
Hydrogen.
hydrogen. Yep, hydrogen on the double bonded carbon, like that. Okay. So now,
Mm-hmm.
do you have this picture? I can send it to you through Discord as well. But do you have this picture?
Yeah, I took a screenshot.
Okay. Using that graph right there, um, where would the alkene show up at in the IR?
1600.
Yeah. So yeah, 1600. That's right. 1600. It's gonna show up around 1600. What about this sp2 CH bond? sp2 CH.
Um,
That
sp2.
would be the 3100.
Yep,
Or yeah.
3100, right? And it's gonna show up as a sharp peak, sharp peak. What about this alcohol group?
That would be would would that be 3300?
Yep, it would be at 3300.
Okay.
And it's gonna show up as a broad peak.
Mhm.
What about this carbonyl here? Carbon double bond oxygen.
That would be 1700.
Yeah, around 1700 as a sharp peak, right? So we could cross out A because A is around 1700. We could cross out B because that's around 3300. So the 3000 range, like I said earlier, that's always almost gonna be there because that's like a regular sp3 carbon hydrogen bond, which is around 3300, and it shows up as this jagged peak, and we could cross out D. So the answer would be C because this is like way too high. Like that's like way too high. 3400 to 3600, 3650, that's way too high.
Okay, that makes sense. So,
Uh-huh.
like, let's say I was given this on a quiz, or like exam again. What would you suggest that I write? Because like I know that when having like a flashcard, I want to like conserve the amount of space for like stuff I really do need.
Yes,
Yeah.
this chart here, this chart would summarize a lot of things for the IR,
Okay.
right? Because you have that chart, you could do that whole process that we just did,
Right.
determining the functional groups present on the model. And then once we have the functional groups present, we refer back to that chart on the note card, and then analyze what it would look like in the IR, and then we could just like cross out, like depending on what the question is, answer it from there. Right. So this chart here is like really important. Yeah.
Okay, thank you.
Yeah, no problem. When did you learn the IR? Like, did you learn that like this week or last week?
It was last week.
Oh
So
shoot,
we
yeah.
get
I,
it
I
for
think
like for like we get a quiz for the slides that we go over from last week.
Oh yeah, so the quiz is based on last week's material. I see, I see.
Yes.
Uh,
Yes.
okay. Yeah. Dang, Way is like ahead of Farhat because I think they didn't start AR yet. I think they're starting that tomorrow.
Really, we're
Yeah.
this week's discussion we covered something like I don't even like know how to explain it. NMR and
Oh,
chemical shifts.
HNMR and synthesis.
It's like the movement of like nucleuses and
Oh,
radio
nucleophile,
waves.
electrophile,
Yeah,
mechanism.
and like SP ways that she's like gonna really emphasize as like hybridization
Yeah.
on midterm too. So I mean I guess that has like some sort of correlation to like what we just like what you just covered right now. Um, it's just a little tricky because it's like I guess you have to really visualize the difference in bonds. And like there was like a chart, it's labeled table of HNMR chemical shifts, and my TA
Yeah, yeah, yeah. It's just
he was suggesting to really
like this and
write
like
it
that,
down.
and it's just like,
Yeah, so
and
a
then
bit
something like this.
scary.
Well,
Yeah.
so that all goes into the spectroscopy section because a lot of these here are like what you're going to see mostly at the end of 118A, all of 118B, and 118C.
Mm-hmm.
Like the different reactions, and you have to predict what.
Oh.
Um, yeah, so these are like the different kinds of questions that you get mostly in OChem. Mechanism is when they give you the reactant, reagents, and the product. So everything, like how to react it into the product using reagents. But for mechanism, you have to show like the arrow pushing like steps on
Oh.
how that
Mhm.
happens. That's the mechanism,
Right.
like where the electrons are flowing to.
Mm-hmm.
Now synthesis, this is where they give you a reactant molecule. They don't give you agents, and they give you a product, and you have to use multiple reactions, transform that reactant molecule into the product like that.
Mm-hmm.
So you do know the reactant and the product, but you have to figure out the steps necessary to transform that reactant to the product. And that comes after when you learn a lot of reactions. And then think of those reactions as a tool, like tools in your toolbox, so then you could use to transform something into something else. So you're probably going to do this last synthesis.
Mm-hmm.
Um, that's my because you're going to see like there's a lot of patterns that show up, and you could like there's multiple correct answers that you could do, not just one correct. Yeah, you can be creative with it. And then spectroscopy is like what we're hitting on now. Like the beginning is IR and then HNMR, and then you'll learn more about CNMR in B when it's in B. Yeah, right.
Yeah.
And then
He also
everything before
has,
this is the fun
yeah.
bits like resonance, acid base, Newton projections, stereochemistry. Like, all that's the fundamentals. It's still important though because that does come back for like reactions and under mechanism, right?
Yeah, she
But
did bring back acids and bases.
uh-huh.
But she already went over SN2 and SN1.
Oh, she went over that already? SN2, SN1, and you too? She went over that too?
Yeah, which I
What?
am a little bit confused on.
Oh, that's usually introduced in like later, but dang, she's fast. She's moving fast for some reason. But when it's in A,
Mm,
but that's
yeah,
like
I
towards
have
the
no
end.
idea.
Okay. Oh, actually, no, that kind of makes sense because you have to like learn about alcohols, ethers too, and then synthesis. Yeah. I see. Okay.
Yeah, not sure, but I'll upload the notes for I guess next time.
Yeah, and then tomorrow we'll hit IR more. So then, um, we could do because I think Kathy's starting IR tomorrow, so we can do that IR.
Okay.
Yeah, that's good.
Thank you.
Okay. Yeah, no problem. Well, let's move on to 180. Um, let me pause. Last session, I think we ended with the Birch reduction reaction to phenols like them, the reactant rearrangement, redox of benzene diol and arene diazonomer salts. Okay. Did Fred finish 22 yet? Uh, uh, in lecture.
I'm not too sure, but I can
Uh-huh.
check where he's
Okay,
going.
okay.
I
I
haven't
see.
felt inclined to watch his lectures yet. I'm not.
Yeah. Wait,
Uh,
when is your next midterm?
Our next midterm is at the end of the month.
Mm-hmm.
Um, but to be honest, I'm not too sure if I'm ever gonna get around to watching those
Yeah,
yes.
I see. Like
Yeah.
towards the end of the month, like once I have like more things together, then you could come to hear more, and then I might do review sessions for you and see as well if I have more time.
Yes,
But
yes, that would be
yeah.
amazing.
Uh-huh.
I think he probably barely started chapter 23, but looking at this, it's like aldol condensations
Hmm.
and Levens did cover that over the summer. So
Uh-huh. That's good.
look,
Yeah, our conversation is more of a 118B thing, which is the introduction. The new thing for 118C is Kleisen condensation, right?
yeah, but he probably didn't get to that.
Okay. That's good.
Yeah.
That's good. Yeah. So let's do phenols. I think nomenclature is more straightforward. You could practice that. But for acidity of phenols, we kind of went over this last. Oh, phenols are more acidic than cyclohexanols because their conjugate base is going to be more stable, right? If I were to draw out the conjugate base of a phenol, this negative charge on the oxygen is more stable than the negative charge on this oxygen over here, right? Because this is able to do resonance, making phenol more acidic. Okay. Next one. Oh yeah, and we also talked about. Oh yeah, I remember now. We went over the rank the following molecules in order of acidity. One is the most acidic, 5 is the least acidic, and I give you like the different EWGs, EDGs, and an empty ring with no other groups attached to it. Let's now go over nucleophilic aromatic substitution, right? Which is a way to prepare phenols. Nucleophilic aromatic substitution. So this is gonna say that when we have with a good leaving group, like let's say bromine, and we have a strong electron withdrawing group, like NO2 ortho para to that, and we put some kind of strong nucleophile, we'll substitute the good leaving group with whatever the strong nucleophile is. The requirement for the reaction here is that there's three requirements. Let's see. Here. Yeah, two requirements. Actually, you need a good leaving group present. Good leaving group. Then you also need at least one strong electron withdrawing group, ortho or para to the good leaving group. Right? And then you could also consider this as a requirement. You need a strong nucleophile. Or actually, no, yeah, any kind of nucleophile would work, like water in neutral would work here, right? So for example, if we have this good leaving group here, bromine, and we have strong EWGs ortho or para to that, and we introduce it to some kind of nucleophile, that's going to substitute the good leaving group with the nucleophile, like this. Right. And here's the mechanism of this problem. Wait, let me give you a more specific example before I give you the mechanism. Let's say we have the structure here. We have EWG there, EWG here, and we react it with these reagents. H2O, H2CO3, 100 degrees Celsius. Our nucleophile here is going to be the water. So first, we have to see our benzene ring. There's a good leaving group present here, which is this chlorine. We have two strong EWGs here, and they are ortho to the leaving group, and we have our nucleophile here. So this fulfills all of the requirements for nucleophilic aromatic substitution. So that's going to substitute the good leaving group with the nucleophile. So it's going to be OH right here, right? And NO2s will stay the same. Yeah. Hi, can you cover electrophilic aromatic electrophilic addition? Yes. Wiley, are you from 118C UC Davis, or like where did you like find this reading? Like, sorry, like from Rand, okay, okay, okay. Yeah, addition, electrophilic addition. Oh, you're in 128A. Oh, do you mean electrophilic aromatic substitution? Like when you have a benzene. Oh no, I think alkene reaction, right? Like when you have an alkene like this, and then you react it with alkene reactions. Okay. Yeah, we could go over that too, electrophilic additions of alkenes after we do some problems. of this, and I want to show you a different reaction for this first, but we'll go over that. Yeah, Levin's taught it today, but I don't have much practice. Okay, yeah. If you have problems on that topic, you could email me those problems to this email. If not, I could just come up with random problems for us to try and walk you through those problems and teach you the reactions. Yeah, okay, just do random problems. Okay. Yeah, I could do random problems. I'll do that after finishing up the reaction and we'll... Oh, you're getting tested on this Friday? Shoot. Like, is it just alkene stuff or like what other stuff is tested this Friday? Electrophilic addition and what other stuff? Let's see. Okay, yeah. So, okay. Yeah. So let's move on to like the electrophilic addition stuff. But first, let me give you one problem, Rand, for you to try, just to finish off this reaction.
You're right. Thank you.
Yeah. And I'm gonna give you the hardest example that I've seen so far for this reaction that I've seen from certain professors. Um, how to think about this. Okay, if I give you that reactant, hmm, okay, if I give you this reactant molecule here, what would you predict the product to be?
You know, this is a really great question that you ask. Um, because before when you had the isopropyl group, I was like, oh, the chlorine would be the leaving group because it's orthopara to the two electron withdrawing groups. But now
Uh-huh.
both bromine, chlorine, and chlorine are. Oh wait, hold on. Actually, let me think.
Uh-huh.
This is a great question. I
Tricky,
think
tricky, huh?
yeah, it's tricky. I feel like though between chlorine and bromine, I would stick with bromine because
Bromine?
bromine, yeah, I feel like bromine would be the leaving group and you would replace it with NH2, but I definitely could be wrong. This is an amazing question that you've come up with.
Mhm.
Chlorine could also leave because I know two is really
Right, right.
oh this is this is a difficult question. I think I'll go with chlorine actually.
Yeah, think about the requirements here. The three requirement, I mean the two requirements
Yeah,
for nucleophilic association, good
must
leaving
be
group, and at least one strong EWG ortho or para to the good
yeah. Chlorine has the ortho and para.
ortho
So
and para. But let's look at bromine. Right, bromine here
yeah,
has no strong EWG ortho or para to that. Right, because if
yeah.
I X out the ortho and para positions relative to the amine, EWG is relative to that bromine.
Mhm. So it has to
So the bromine here will not be substituted. It would be the chlorine that gets substituted.
Yeah, that
Yeah.
makes a lot of sense.
But even though, remember back in 118A, we said bromine is a better leaving group than chlorine because like, it's a bigger atom size. It's able to leave
Yeah,
the like, negative charge. This one, nucleophilic substitution. Know that because we have benzene ring and good leaving groups on that benzene ring and EWGs on the benzene ring. But then if we have multiple, we have to choose the leaving group that has the strong EWG ortho or para to it, which is the chlorine here, right? Ortho, para. The strong EWG, strong EG. Right.
yeah. I was thinking at first like, oh, bromine is going to be a better leaving group than chlorine, but then I
Uh-huh.
was like, oh, the ortho para groups are to chlorine, not to
Yeah.
bromine.
Yeah. That's why I changed up the halogens just to try to trick you.
Yeah, it works.
Yeah. 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 Let's see. And then this might show up on your homework or practice as well, but we'll see. We'll see. Right.
Yeah. Probably showed up on one of Levin's practices from
Yeah.
the
Levens,
email chain.
Helix, and
Okay.
Nisiri. This showed up for all
Oh,
of them.
man. Oh, lovely.
Yeah. But Fahrenheit is
Hmm?
new, so not too sure about him yet.
I feel like he would maybe not give this type of question.
Mhm.
I don't know. He doesn't seem like that type of professor. He gives us easy questions and then somehow our average is so low. So
I know, I know. Like it's
like
very
everyone
similar
was
to the
like,
practice too. Like
yeah, yeah, everyone was like, oh, that exam was so easy. And I was like, oh, that exam was so easy. Maybe I missed like 2 points.
and then
And
the
then
average was 59.
yeah, oh, multiple choice was bad.
Oh, multiple choice was bad. I see.
Yeah, I think
Yeah,
we're all just used to written responses.
I know. And but did you finish the homework before the exam, or did you do the homework after the exam? Did you finish the homework after the exam?
Well, I did two of the chapters and half of 21 before the
Uh-huh.
exam,
Yeah.
but then for the rest of 21, I was like, I
Uh-huh.
can't be asked to do this right now, so
Yeah.
I just did
Studied
it.
instead.
It
That's
was so
good.
long.
I know. 50 questions each, 150 questions total. It's
Yeah, and then the 150 questions from the practice.
oh yeah. Oh my God. Yeah. Prioritize the practice. Like it's very similar to the practice and
Yeah,
understand
he's
each
very
practice
generous.
too. Yeah. Uh-huh.
Thank you so much for your help today.
Yeah, no problem, man. Okay. Um, so the test this Friday you have on 128. Wait, who's your professor for 128A? Why Riley? Oh, Riley. Levens. I see. Oh yeah, okay. Relationships between isomers, optical activity, chiral environments, acid-base definitions, identifying types of acid bases, acid strength, neutralization, pKa. For Levens, it's a big pKa. Like, so, does she allow note card for your exam this Friday? Yes. Okay. So for a vocab question, it's probably gonna have like, what pKa does functional group have? What pKa is that? So make sure to have those pKa down on your note card. Yeah, that's good. That's good. Terms and vocab about mechanisms, properties, and structures of alkenes, IUPAC nomenclature, stereochemistry of alkenes, drawing mechanisms, electrical addition to alkenes, and hydration of alkenes. Okay, there's a lot of alkene reactions. HBr. But I'll just try to teach you from scratch of what I like know about it, and then I could check my notes to see what I'm missing. But from the basics, here is a basic alkene right here, a carbon level one alkene. Okay. And this is going to react with HBr, HX. So if I were to name this reaction, this is going to be hydrohalogenation of alkene. I've seen some professor just say as addition of HX to alkene. Where X is chlorine, bromine, strong to alkene. have you learned about carbocation stability and which carbocation is going to be more stable? Like, let's say I give list right here. Yes, hyperconjugation. Right. The more substituted the carbocation because of hyperconjugation. Think of it as like these positively charged carbons here are missing electrons, right? So think of the groups as like of the carbocation. The less lonely it is, more stable it is, right? But then this primary carbocation here has only one R group, so like that's like one friend, more lonely, less happy, less stable. The one that's even less stable than that will have no friends, like just that methyl carbocation right there. That's the least stable carbocation that we have because it has the least substitution. Yeah. Yeah, shifting or something. Yeah, that's important because you have to know this list right here because that list will tell you if you need to do a hydride shift or alkyl shift or alkyl shift. And then Elisa and Kathy, you will learn about this in SN1, E1 soon. Elisa's starting that now. All right. So now I just gave you this basic example right here. If you see a carbon double bond carbon like that, these are very electron rich, right? There's a lot of electrons in this bond, in this like region, double bond region, right? So I could either push the two electrons onto this carbon, which would give me resonance structure here, or I can push my two electrons onto giving me this resonance structure here. Wait, this should be positive charge. This should be a negative charge, like that. Okay. So based on the carbocation stability that we just talked about, which carbocation is more stable? The pink one or the red one? The red one on the right. Yeah, that's right. Because this carbocation here is more substituted than this carbocation right here. So this is actually going to be like the more major resonance structure compared to the pink one. And that's going to show that nucleophile is going to be this less substituted carbon there. That's the carbon that's going to attack the hydrogen from the HBr because their negative charge is going to be there. So this pair of electrons here is going to attack that hydrogen, right? It's trying to make a new bond between this carbon and that hydrogen. And then when that happens, as the bond is being formed between that carbon and hydrogen, this bond between the hydrogen being pulled off by that carbon is going to break and go onto the bromine like that, right? And that's going to give us this intermediate right here where we still have the positive charge right there. And now, just to make it clear, I'm going to circle the hydrogen in green, which is that hydrogen in green right there. But you could have left that as invisible as well, but I'm going to make it clear on where that came from. Wait, why does the hydrogen get attacked by the lone pair? Yeah, so the hydrogen is going to get attacked by the lone pair because think of HX as a strong acid. This is HBr, strong acid. Right? And then think of the alkene here as your base in here, right? Carbons can use to attack. It can use either this carbon or the more subcarbon or less subcarbon to attack. The reason why I'm using the less subcarbon to attack is the base carbon is going to be the base, and this is going to be the acid. Right? We're acid reaction here. This base is just grabbing that hydrogen like that. The reason why I chose the less subcarbon to grab the hydrogen is because that leads us to the more stable intermediate, more stable carbocation intermediate. Right. And now, once we have that more stable carbocation intermediate, carbo, you have to stop and see if you could shift this carbocation to anywhere more stable. And you can only shift it one spot right or to the left. That's going to be less stable if we shift the carbocation there. So we don't want to do that shift there. If you look to that's going to the carbocation to the less stable position. So that's going to be unstable as well. Right. So now once we have that stable carbocation, the Br minus is come back and attack carbocation, right? This Br minus here came from that HBr being broken off, forming this final product here, right? And now I'm just gonna leave the hydrogen here as invisible, but that hydrogen is still there. And that's the final product of this. Okay. Final product for only the red side, right? I did draw the pink side because we said that this is the less stable carbocation intermediate. So we are not going to go with that route, right? And this is going to be our major product, our only major product. Lab is not like 100, it's major, like majority red. You could say like 90 something percent, 92, 93%. The other percent, like 7% is going to come from like the BR is going to be here instead, but that's minor. But in the test, she's going to ask you to draw the major products only, which this is as the final answer for major product, only in red, the one in red. The way that I drew the mechanism is kind of like really long, right? But if you were to draw out the mechanism like normally, this is what you would do. You would first figure out which carbon would be the more stable carbocation, the more substituted one right here, meaning that your less substituted carbon is going to attack the hydrogen, kick out the Br, have a positive charge on that carbon right there that lost the bond. This carbon here gained that maintained its bond, so that's why it's still neutral. And then the Br minus that got kicked out is going to attack that positive charge to give us this final product here. And this is the simplest example because we had no hydride shift, no alkyl shift. But I have to draw out the intermediates and stuff. You don't have to draw out these intermediates if it was just a predicted product problem. So if the problem was asking you to predict the product of the following reactions, and she gave you this reactant and reagent, you just draw what is in that box right there, the final product. But if the problem is asking you to draw the mechanism for this reaction here, where she does give you the reactant, the reagent, and the product, then your answer would be this right here. But you would have to draw out all the arrows and draw out all of the intermediates that leads to that product right there. So it just depends on what your problem is, what the question is. Yeah. Yeah. So tomorrow we could go do more complicated examples and do more like reactions. But tomorrow it's probably gonna be pretty hectic because I'm gonna go over IR, Kahoot as well, electrophilic reactions, and maybe some 118C stuff. But we'll see. We'll see. If is there a difference between the top and bottom for the arrow? So the difference is that this is what you would put on the exam, the bottom one, because that's the way it's normally drawn out, where you know that this bottom carbon here is the one grabbing the hydrogen because that leads to the more stable carbocation. That's why you're not like using this top carbon to grab the hydrogen, right? Because if you were to do that, you're gonna get this carbocation right here, the less substituted unstable carbocation. We don't want that. The one on the top is just me explaining like why the bottom carbon, the less substituted carbon, attacks the hydrogen or the electrophile. Right. You don't have to actually draw out this resonance structure here. You could just go straight from the attack, straight to the attack. Use the less substituted carbon and attack the electrophile right away. Right. This is an over explained way to do it. Yeah, no problem. Okay. So my office hours is like ending now, but you guys can come back tomorrow and we could go over more specific examples and do AIR Kahoot. Yeah,
Thank you.
no problem. Yeah.
Have a good night.
Yeah, good night, Elisa. See ya.